Okay. Bismillah ar-Rahman ar-Rahim. We'll begin now. We studied vector fields in section 16.1 and what is meant by conservative field, which is the gradient or the del of some scalar function. This is what we have here. A vector field capital F is conservative on some open connected region if and only if it is the del or the gradient of some scalar function little f. This may be written gradient of f. F may be a function of two variables or f of three variables and so on. This is what we have in calculus 3 for some differentiable potential function. This means that if f is m in the direction of I, and n in the direction of j, and p in the direction of k, is the del of some f. Say it's function of three variables. This is by definition is partial f partial x, partial f and partial y, partial f partial z. This means that m is partial f partial x, and we have studied how to find this scalar function, and we called it a potential function for the vector field. N is partial f partial y, and p, the last component, is partial f partial z, and so on. From this assumption, if this is satisfied, we can determine some potential function f for this vector field. Next, the second lecture, the second section of chapter 16, vector fields, we have studied line integrals, where we studied two types of integrals. This was from section 16.1, vector fields. From section 16.2, we studied line integrals of the form f of x, y, ds, which gave us the area of some curtains determined by this function f of x or y over the curve given over some curve defined parametrically on the xy plane. And we studied the line integral of a vector field dr over some curve as well. And we mentioned that this means physically the work done by this vector field along to move a particle along this curve C. This is a general definition of the work done by a vector field or force field along some curve in general. This was the extension of the definition of work. Instead of motion along straight line, we move now along a curve C. Today, we will combine these notations, the line integrals and the conservative field, and we get what we call the fundamental theorem of line integrals. Fundamental theorem of line integrals, or the line integrals of conservative fields. This gives a special extension of the fundamental theorem of calculus we are familiar with from calculus 1. These are some of the examples we studied last time. We find the integral of this f along such path formed of the union of these two paths, C1 union C2, as you see, C1 union C2. So to move a particle from this point to this point, then to that point, we calculate the line integral of this force field along this curve C1 union C2. So we calculate part of it. Along C1, we make parameterization of the curve, or here it's a line segment, y equals x. We make easy parameterization, and then along the second path C2. Then combine this or add these two works to get the total work. The question is, if this field is conservative, if this field satisfies this condition of having potential what happens for this integral? The idea is the line integral of a conservative field along a curve does not depend on the path. If we move along line segments, if we move along an elliptic curve, if we move along a circular curve, if we have the start point and the end point the same, we get the same result. The work does not change, For example, this was the case here. If you have this vector field, y, in the direction of I, x minus x in the direction of j, we have sketched this vector field and the circular path given by this curve. You can check if this vector field has a potential, or in another language, is it conservative vector field? This is easy, we've done this last time. Today, we'll have this is the fundamental theorem of line integrals. I remind you is this fundamental theorem of calculus. What is it? We state it in this form. If we have continuous derivative for the function f of x, of course, calculus 1 is functions of one variable x. So if we have continuous derivative f prime of x on some interval a b, then the integral, the definite integral from the point A to point B on the interval from A to B of the derivative f prime of x dx, I mean the integral of the derivative. Of course, we know this is f of b minus f of a. The value of the function f at the end point b minus the value of the function f at the starting point a. Of course, we are used to this form. We write it f of x and write these brackets from a to b. And then substitute from the upper bound minus substituting from the lower bound. This is the same as this. Again, why is this? Because we integrate the derivative. So integration of the differential of a function gives the function itself, because we have the antiderivative f. What is the function? The question is, what is the function? Whose derivative is f prime? Of course, it's f itself. This is easy antiderivative. So we get the value of the function at the upper bound minus it. This is old information for us. We studied this before, long time ago in calculus 1, or even in high school calculus. Now we extend this to our new idea of line integration over a curve. The fundamental theorem of calculus, this is what we have here, is naturally extended today to fundamental theorem of line integrals. What is line integral? Again, this is line integrals over the curve C, or capital F vector field dot dr over the curve C. And this is the situation exactly we have. This is, and it has this nice physical meaning of the work done by this vector field or force field to move the particle along this curve C. So this nice application. So what the theorem states exactly, it says if we have a vector field f of x, y, continuous conservative vector field, if we have a continuous conservative vector field, what is conservative? Again, it is the gradient of some scalar function little f of x or y. If we have this situation, like think of what? Think of the capital F is the derivative of little f. Like what we have here, this is the derivative of f, derivative of little f. Think of the del operator or the gradient operator as extension of the differential, the prime here in calculus 1 story. So what happens when we integrate this capital F along some curve beginning from A to B with some restriction on the curve to be smooth curve from parameterized by T, which start at little a and ends at little b. This is what we have exactly. Integral of this vector field f dot dr over this curve is equal to the potential function at the end minus the value of the potential function at a. Again, this capital F is conservative field. What does this mean? It is the gradient or the del of some scalar function little f. So think of it like this. Like this is f prime. Instead of this prime, we have this del operator. So what we get is the original function, little f, at the end of the curve, at the end of the interval before in calculus 1, minus its value at the beginning and the start of the curve. So this is the analogy between the fundamental theorem of line integrals, integration of a curve, and the fundamental theorem of calculus, which is integration over x as usual. It's not only that, it is used in the proof of the fundamental theorem of line integrals. The fundamental theorem of calculus is used to prove this generalization or this extension as follows. Let's prove it. It's nice proof. If we have this, if we need to calculate the integral of this capital F dot dr over the curve C, the smooth curve C, we can use the parameterization. F is a function of x and y and z, or xy only, which is parameterized by the position vector r of t on this curve. So we write this capital F explicitly as a function of t, and make this dr dt thing. This is the same as dr. Why we do this? Now we use the given condition. This is given that this extension and this theorem applies only for conservative fields, which are the fields having potentials, or the fields which are the gradient of some scalar function little f, like this. So substitute for del f instead of capital F to get this form. It is del little f of r of t. Again, now we can apply the chain rule of multi-variable calculus. This is we have before in chapter 14, I think. So we can write this as d by dt of f of r of t. Why chain rule again? Why chain rule of differentiation in 3 or 2 variables? Because we have x, y, and z of the vector value, the curve, all of them depend or parameterized by t. So x, y, and z are hidden here in terms of t. So we can have this. Now this is calculus 1 story, d by dt of some function of only one variable t, dt. So we use now the fundamental theorem of calculus from single variable. So it's what? It is the value of this. This is the antiderivative of this integration. So it's f of r of t on this curve. This curve is given by this. This curve, C, begins at t equals little a at the point A, capital A, and ends at the point at the time B, the parameter I mean, which most of the time means the time actually, which ends at the point B of the curve. So it is the value of this little function, little f, which is the potential, the scalar function, the f of r of b minus f of r of a. Again, r of b is the point B, capital B on the curve, minus r of a, which is the point capital A on the curve. This says what? Says does not depend on the curve. We didn't actually needed to use the parameterization of the curve or to know even what this curve is. So the value is the value of the potential function at the end of the curve minus the potential function evaluated at the end of the start point of the curve. Again, we come to the same form of the calculus 1 fundamental theorem of calculus. Again, here we can write this. f of r evaluated from the point A to the point B, and begin substitution as usual from the upper bound minus substitution from the lower bound. This is the similarity, and the important point is that we have used this fundamental theorem of calculus from calculus 1 to prove its extension into the fundamental theorem of line integrals, which is the integration over curves in calculus 3. This gives directly some very important corollary result from consequence of the theorem, which can be written in this way. The integral of, look at here, be careful that, be sure that this integrand or the vector field capital F, when we integrate over C, this only applies when this F is del F, little f. So we distinguish between the capital and the little one. We use the capital F instead of the del of the little f. This is the potential. Potential function of the vector field capital F. So you need to be very careful about this distinction. So if this capital F is in the form of del F, we can apply this fundamental theorem of line integrals and evaluate the value of the little f, the potential at the end point of the curve, minus subtract the value of this potential function at the starting point of the curve. What happens if this curve is closed, simply connected domain like this ellipse, this region D? What happens if we integrate from the point A and go anti-clockwise till you get to the point B, which is A itself again? The mean, the starting point, the end point is the same as the starting point. So it's a closed curve, but simply connected means does not cut itself. You don't have this form, for example. The curve is not cutting itself and has no holes. It's simply connected, does not have this such a things. So it's simply connected, closed, simply connected domain. What happens? The result of this theorem is that this integration over this loop or closed connected domain, simply connected domain, is 0. Why is that? Because the value of the f of A minus f of B is what? Because B is the same as A, because the end point is the same as the start point. So FA minus FA gives 0. So if we know this information about the integrand or the vector function to be integrated, capital F, if we know it's conservative, we have these very important results. We does not, the value of the integral does not depend on the path. And if the path is closed inside this simply connected domain, the value of the line integral is actually 0. So this is very nice and important result because it simplifies our life and makes the calculus easy. For this, we are interested in conservative fields, as we mentioned in the last 2 lectures. Okay, these are the remarks about what happened to simplify what happened. This means that the integral depends only on the 2 endpoints and does not depend at all on the path. So if we have f conservative and we need to integrate it over this curve C, and someone else need to integrate it on another curve C1, C2, going from A to B, the result will be the same. C3 gives the same result, and so on. The integral of f dr dot dr on the curve C does not depend on C itself. It depends on the initial point and the final point only. If A is the same as B, we get 0. Note this condition again and again. This does not apply to any vector field but the conservative ones. And there's the other condition about the curve itself has to be a smooth curve, defined parametrically by differentiable functions. So now to make this long story short and simplify, let's combine what we know about these conservative fields. By definition, they are, okay, first of all, we have defined it in section 16.1 that the conservative fields, capital F, is what is defined by gradient fields. It's a gradient field. Of some scalar function. F, x, y, z, or x, y only, according to the situation. What is the gradient field? It is the vector field of derivatives, partial derivatives with respect to x in the direction of I, with respect to y in the direction of j, with respect to z in the direction of k. What we get today, additional information, is it's path independent. Integral of conservative field is path independent. When we integrate gradient field, which is capital F, this capital F, which is again del F dot dr, we get from on a curve C beginning from A to B, we get FB minus FA. This is what we call fundamental theorem of line integrals. Third information, we used it last 2 lectures ago to find the potential function, but was in 2 variables. Let's have this general situation now. Let capital F be Mi plus Nj plus Pk. Then we have this condition. This is a necessary and sufficient condition with some additional restrictions. What happens? We have to have this. This is the part of the vector field in the direction of I. It's a function of x, y, and z. What happens if this f is conservative? Partial m, partial y, the part in the direction of x. Its derivative with respect to y has to be, which is partial m, partial y, has to be equal to partial n, partial x. Derivative of the part of f in the direction of y is derivative with respect to x. And so on. Partial m, partial z has to be equal to the partial p, partial y. And so on. The third one is partial p, this part of f in the direction of z. When we differentiate it partially with respect to x, partial p, partial x, has to go the other way and continue to fill the cycle, equal to partial m, partial z. We have to have all of these equalities of partial derivatives. They are very easy to prove. They are a direct consequence of Clairaut theorems, as we'll see now. Let's see. If we have this is a proof of the previous condition. If capital F is del F, little f, we know this is the partial derivatives. And if f is given by m, n, and p in the direction of I, j, k, respectively, then what we have? Then we have this. This is the same. We have to have partial m, partial y equal to partial pi partial y of partial f partial x, because m is the same as partial f partial x. So differentiating both sides with respect to y gives this. Partial m partial y is partial to f partial y partial x. And we have, we have the continuity conditions of the partial derivatives, we can interchange y and x, and they have partial to f partial x partial y. This is what was called Clairaut theorem. This can be written as partial by partial x of partial f partial y, which is derivative of n with respect to x. Look here again. This is derivative of m, the first part, with respect to y, equals the derivative of n, which is the second part, with respect to x. So the derivative of the first with respect to the second equals the derivative of the second with respect to the first variable. We can do this again and find the derivative of the second with respect to the third variable is equal to the derivative of the third part with respect to the second variable. And thirdly, again, the derivative of the third part with respect to the first variable x is equal to the derivative of the first part m with respect to the third variable z, and so on. Again, it's easy. Don't worry about it. It's very easy. Hence, we have this test. We're testing what? How to test the conservative field. We are given a field, vector field, and we need to test whether it is conservative. But we are not asked to find the potential function itself. If we are asked to find the potential, we can find it at once by the method we studied last time, or 2 times before. This is test for conservation test of the vector field, the given vector field. What we have again, partial m, partial y, derivative of the first with respect to the second variable, equal partial n, partial x, derivative of the second part, second component of the vector field with respect to the first variable, and go on, same. Derivative of the second component with respect to the third variable equal the derivative of the third component with respect to the second variable. Thirdly, the same. Derivative of the third component of the vector field with respect to the. This is the third component. Derivative of the third component with respect to the first variable equals the derivative of the first component of the vector field with respect to the third variable. It is circulating like this. You can write it like this. We have m, n, p. This is a cycle. And we have this cycle of x, y, z as the 3 variables. So we differentiate the first with respect to the second to the first, and so on. This nice story. So we have now these ideas about conservative field. We have the question testing whether it is capital F conservative or not. We can use this condition. We can use this condition. Let's frame it. Give it a color. And another question to find the potential function little f. We are familiar with this now. And the third question is to compute line integral of this conservative field, f dot dr over c. We can use now what? We can use the fundamental theorem of line integrals. What is it? It is f of the last point, the end point, minus f of the start point, or its corollary of the curve or the path is closed, and we write this over a curve, close the curve. This is the closed curve of f dot dr. And we know the result of this is 0 if f is conservative. If f is little f, we know this closed line integral is 0. So this simplifies life if we know this is a conservative field. Go back again. So we have the question of to check whether the function or the vector field is conservative. Second, to find its potential. You are familiar with this. Third, to find the line integrals. So let's have an example in details. I'll stop for a minute for the exam. Okay, let's continue. This is the summary of the story behind the conservative field we have till now. We will have more information about conservative fields in the sections to come. We will study the density of these fields and something called curl or circulation of this field in the coming section, inshallah. So let's have this example and do these goals of the lesson. Let the given vector field is given by this vector valued function. We have y cosine x plus y, sine x plus x, and 1 in the third component. So according to our notation, we have m of x, y, and z, n of x, y, and z, p of x, y, and z. In fact, z does not appear, does not show here, and even this is a constant part. Okay, the condition is fine. We can check the condition. So let's check the first condition. What is the condition again? If we differentiate the first component m with respect to the second variable y, what happens? Let's compute partial m partial y. So the y is considered the variable and the x treated as a constant. So we get cosine x plus 1. The derivative of y with respect to y gives 1. Okay. What happens for the second component of the vector field? Let's differentiate it with respect to the first variable. Okay. This is m and p story. These are the three components of the vector field, vector function. And these are the first, second variable, third variables, x, y, and z in order. Differentiated the first with respect to the second. Now we differentiate the second with respect to the first. How we do that? What we do, differentiate n with respect to x. What we get? Cosine x plus 1. That's it. They are the same. Yes, right. They are the same. This say partial m partial y equals partial n partial x. That's fine. Not enough. We need to do the second with respect to the third and the third with respect to the second. Of course, the stated first is the component of the function, second is the variable. So let's compute this. This is easy because here is 1. Z, the third component, p is 1. So its derivative with respect to y, x, and z will be 0. So this makes life easy. Partial p partial x is 0. Partial p partial y is 0 as well. So let's find partial derivative of the second, which is n, with respect to z is 0. And the partial third component, p, with respect to y is 0 as well. I made third step instead of the second. It will not matter, in fact, because everything here is 0, as this is constant. Derivative of this with respect to x, y, and z are zeros. So, and 0 does not show up here. They didn't appear. Z does not appear here. So derivative of m with respect to z is 0. Derivative of n with respect to z is 0. So our requirements are satisfied. So we have what? We have this story again. This is the condition. This is the easy condition for the conservative field. In terms of the partial derivatives of its components with respect to the variables. If it is two variables, it will be easy. We will be missing this part. We have only this part. Because there is no third variable and no third component. So we have only one condition. If the function, the vector field is a function of two variables only. So the derivative of the first part with respect to the first component, I mean, with respect to the second variable is the same as the derivative of the second component with respect to the first variable. There is no third variable to check these two conditions. If we have three variables, we have all of these three conditions. That's easy part. So a very easy check to check the conservation of the field. Is it a conservative field or not? This is easy. We're done. Second, how to find the potential function. We already done some example on section 16.1, assuming capital F is del F, but it was function of two variables. Today we will have similar situation, but in three variables. But in fact, in two variables again, because that is not appearing, but let's treat it as if there is Z there. Okay, let's go on. Second, what is the requirement? To find the potential function little f. Distinguish clearly, please, between the capital F, the vector field, and the little f, a scalar potential function. Okay, assume again, same method again. Do it in details again, please. Why we care about this scalar function and this potential function? Because of the fundamental theorem of line integrals. Say, give me what? Give me the integral of this vector field from point A to point B on a curve in terms of the value of this potential at these two endpoints. F at the end minus f at the beginning, little f. As if we were in calculus 1 dealing with the antiderivative of the integral, required integrand. The antiderivative at the end minus and the antiderivative at the beginning. Okay, so let's go in details. Let's assume capital F is conservative. It's not assumed. In section 16.1, we assumed it's conservative. Now we have the conditions and we know, in fact, it's conservative. So F is conservative. We done that. We are done with this. We already proved it is conservative field. Now we know this. Capital F is del of little f. And we need to find this little f. What is the method we studied before? Let's do it again, but for vector function, vector field of three components, not only two. So we have this. Del f is, you know this, del f is the derivative with respect to x, derivative with respect to y, derivative with respect to z. And we are given these components in the form of m, n, and p. So how to find this f? How to find this f? By integrating the first component, equating this is the same. This is the first component of capital F. This is the first component of capital F. These are the same. So equate these and integrate with respect to x. Okay, let's do that. Equate these and integrate with respect to x to find the little f, the required potential function. Therefore, partial little f with respect to x equals m. Therefore, integrate with respect to x. Of course, as if x is the only variable we have. Because the derivative here is with respect to x partially. So we treated, to find this, we treated y and z as constants. So now we have, what is m? We are given n, this is m. This is m, y cosine x plus y. So this is m, y cosine x plus y. Integrated with respect to x as if y and z are constants. So x is the only variable. So the cosine x will yield in the integration sine x and y as a constant, and this constant temporally y constant gives yx plus what, as we mentioned before, a constant. We are used to this, to write a constant, arbitrary constant of integration. But here the integration is with respect to x as the only variable, considering y and z as constants. So there might be the case that there were some functions depending on y or z and upon differentiation partially with respect to x, we get rid of them. They are removed because they depend only on yz, so they were treated as constants and gave zero derivative. So we have to be careful about this and write the function as a function of y, write this supposedly constant of integration as a function of y z. So what about this g? How to find this g? We go to the, we already integrated and found very big part of this is the required potential. We are nearly there, but we need 2 steps more to go. Require the potential function. It is y sine x plus yx plus some function g depending on yz. How to find this little g to know exactly what is the required potential function? Let us differentiate this scalar function with respect to y. Why we do this? To equate it with the second part of the given vector field. And look what is g. So now, after integration and finding f, let's differentiate it. Let's differentiate it with respect to y. What we get? What we get? Consider y the only variable, so we get sine x from here. Y is the variable, so like 5y, we get 5. So y sine x, we get sine x, as if it is a constant. Here, yx gives again x, because we differentiate partially with respect to y. What about g? G, the function we are looking for to finish our, to know exactly what is our potential function, little f. Now, differentiate g with respect to y. What is this? I will know what is this soon. Now, we have partial f partial y. And we have it before. We are given partial f partial y. This is the second component of the big F, the given vector field. This is partial, the potential with respect to y. Partial little f with respect to y. It is sine x plus x. Yes. So let's equate these. We have this information about partial f partial y, and we are given this is the second component of capital F. So this must be the same. We are here now. Using this second equality. We used this first and integrated to find the potential. But there is some missing information in this potential. We will finish the puzzle by studying the other 2 parts, other 2 components. Now, using partial f partial y equals n, we get this, from this equality, we get what is partial g partial y. It's clear that sine x is there. Sine x is there, x is there, so this missing part must be 0 because these are equal. So partial g partial y is equal to 0. This means what? G does not depend on y. G does not depend on y because its derivative with respect to y is discovered to be 0. So what is g exactly? G was supposed to depend on y and z. It does not depend on y, so the remaining variable is z. So g must be a function of z only. Does not depend on x, does not depend on y. This is the second discovery. Let's see what is the state of its dependence on z. Now, again, so g is g of z only. We can write this, our scalar function again, our scalar potential function, little f of x equals sine x plus g of z. It was g of y of z before, g and y, g of y and z before. Now we know that it is g of z only. So what happens? Let's differentiate again, the same story. Differentiate now. So once we differentiated with respect to y to get some information, now we differentiate with respect to z and equate the third components to get the missing information. So partial f partial z, there is no z here, this gives 0. There is no z here, this gives 0. this is g prime of z, because we're differentiating with respect to z, and this is only one variable. So we can write it dg by dz as usual, or g prime of z. So, and from the third equality, this must be the same. Partial little f partial z must be the third component of f, which is p, which is given 1. This is the third component of capital F, 1. So what we get of these equalities, g prime of z equals 1. What we get from g prime of z equals 1? Of course, this is easy equation. The derivative of some function of one variable z is 1. So integrating with respect to z, we get gz equals the integral of 1 dz, which is z itself. Plus, of course, maybe some constant. Now it's a constant. Constant, pure constant, does not depend on any variable. So we can consider this 0, because it will not matter. In fact, why? We can consider it 0 simply because our line integral on a curve C of a conservative vector field del F is equal to little f at the end point minus little f at the start point. And this, if there is a constant C in this potential function, will be here. It will be here minus it will be here as well. So it will cancel anyway. So it will not matter at the end of the day. So consider it 0 for simplicity. This in the story. Therefore, we discovered our potential function f x, y, and z equals y sine x plus z. This is the methodology behind finding the potential function, scalar potential function, little f, of a conservative vector field, capital F. What is the use of this? How to use this? What is benefit behind this? This is exactly what we need to apply our fundamental theorem of line integrals. This is finished. This is the end of question 2. We already found the potential of this conservative field. Thirdly and lastly, let's compute the f dot dr, capital F, the vector field, force field, any field dot dr along some given curve from the point 1 to 1 in space to the point 1 by 1, 3 in space. So what is the why 3 variables? Because we are given this vector field, capital F, in 3-dimensional vector field. So we are asked to find this line integral of a vector field, capital F dot dr along some curve. These are the points. Let this be A and this be the point B. This point to this point. What is the curve? In fact, he didn't give me a specific curve. And this in itself is a clue. This in itself is a clue about the solution. Because if it does not depend on the curve gamma or C or any curve, so if he didn't give me a curve, this may mean that the value of the integral does not depend on the curve. Wherever you go, move on any path on the curve C or the curve gamma or the curve beta, whatever. The result depends only at the end points, the beginning and the end point of the curve. No specific curve is given. Even if we are given a curve, we need to check the conservation of the field. If it is there, this simplifies our calculus of integration and so on. We have more information to come in the coming lectures, inshallah. This in itself is a clue for using the fundamental theorem of line integrals. Why? Because this integral, I know the result of this integral. Because this capital F is del of little f, and the result will be the value of the antiderivative or the potential function in our new terms at the end of the curve minus the value of the potential at the beginning and the initial point of the curve. So this is how to answer part 3. This is the whole story and the whole theorem of today. Line integral of a vector field capital F, which is conservative, means it is del of F or gradient of F is the value of the potential function. F of R of T. F, which this is the value of F at the end point, which is B, pi 1, 3, minus the value of this potential function at 1 to 1. Plug in these values in the function. What is F little f? This F little f is what we discovered here, the potential function by the method studied before and repeated today for more revision. This is pi 1, 3, this is the x, 1 is the y, 3 is the z. Substitute here, y is 1 sine pi plus pi plus 3. This is the value of the function. This is the value of the integral equals the value of the function at the end point minus the value of the function at the initial point, 1 to 1. This is plug in 1 to 1 instead of x, y, and z here, you get 1. So this is 2, in fact. This is 2 sine 1 plus 1, which is x, plus z, which is 1. Yes, right. So sine pi, of course, is 0. So this cancel, and we remains here pi plus 3, the z value minus 2. I check again, y 1 to 1, okay. So this is pi plus 3, I write it again, pi plus 3 minus 2 sine 1 minus 2. So this is the result, and we need to simplify. 3 minus 2 is 1. This is 2 sine 1. 1 is not a special angle at all. This 1 means 1 radian, which is approximately equal to 57 degrees, 57 degrees. It's a big angle. It's not a special angle. It's not pi over 6 or 4 or 3 or this nice simple angle, which gives rational values. This gives irrational and transcendental numbers. This can be approximated, but we leave it here as an exact form number. 3 minus 2 is 1. And this is my final answer. Think if you are given a specific curve and the integrand or the vector valued function capital F is conservative, and you go for parameterization and this long story made last lecture, and they miss this nice easy computation and miss the benefit of the conservative fields. So think about it. If this function again, the fourth requirement, if you are asked to find the line integral of this vector field along a closed path, what happens? This, of course, will be part 4. F dot dr over this curve, closed curve, lying on some closed, simply connected domain. For example, this simply connected domain, circle, and this stuff. What we get, this symbol of the circle or the ellipse drawn around the integral sign. This is the consequence of the fundamental theorem of line integrals is 0, which physically means that the work done by this field to move particle from a point along a closed curve in this domain is 0. And we'll stop here, and I leave you with your worksheet to finish your time of the lecture. See you soon, inshallah. Take care.